So what's your general feeling about chapter 11? It's okay. It's so functions of two variables are to be compared all the time with the functions of one variable. Every notion you have seen in Calc 1 has a corresponding in notion in Calc 3. So really no questions about theory concepts, chapter 11 concepts, previous concepts. Feel free to email me this weekend. Don't think it's weekend because okay, we are on a 24/7 availability. People who use web work, not just me, but everybody who uses web work is on a 24/7 availability answering questions about web work problems. Saturday and Sunday is when most of you do the homework. It's convenient for us as well because we are with the family, but we don't have many meetings to attend, so I'll be happy to answer your questions. Last time we discussed a little bit of a preparation for the chain rule in Calc 3. So the chain rule in Calc 3 was something pretty neat. The section 11.5, the preparation was done last time. But I'm gonna review it a little bit. Let's see what we discussed. I'm gonna split again the board into two, and I'll say, can we review the notions of chain rule when you start with a variable, which let's say it's time. Time going to f of t, which goes into g of f of t by something called composition. We've done that since we were kids in college algebra. Well, what, you never took college algebra except in high school. You took high school algebra, most of you. So what did we do in high school algebra? We said G composed with F is a composition of two functions. What I'm skipping here is the theory that you learned then, that they to compose well, the f of t has to be in the domain of G. Right? So the image f of t, whatever you get from this image, has to be in the domain of G, otherwise the composition could not exist. Now, if you have the differentiability, assuming that this is G composed with F, assuming to be C1 meaning differentiable and derivatives are continuous, assuming both of them are C1, they compose well. What am I going to do next? I'm going to say the dt g of f of t, and we said last time we get the chain rule from the last function we applied, g primed, and so you have dg du at f of t, calling this guy u variable just for my own enjoyment, and then I go du dt, but that du dt will be nothing but f prime of t. So remember the cowboys shooting at each other, du and du? I will replace du by f prime of t, just like you did in Calc 1. Why? Because I want to have a mixture of notations according to Calc 1 you took here. The idea for Calc 3 is the same. We saw it last time. Assuming everything composes well and has differentiability and the derivatives are continuous, just to make your life easier, we have x of t, y of t, two nice functions, and a function of these two functions, a function of these two variables, f of x and y. So I'm going to have to say, but x is a function of t and y is a function of t. So I should be able to go ahead and differentiate with respect to t. And how did it go? Now that I prepared you last time a little bit for this kind of new picture, new diagram, you should be able to tell me without looking up the notes from last time how this goes. So I'll take the function f of x of t, y of t, and when I view it like that, I understand that it's ultimately a big function f of t, right? It's a real valued function of t ultimately as the composition, this big F. Okay? All right, so does anybody remember how this went? Let's see. Well, the derivative with respect to t of this whole thing, f of x of t, y of t, was the partial derivative of f with respect to x evaluated at x of t and y of t. So everything has to be replaced in terms of t because it's going to be function. We assume that this variable, this derivative exists and is continuous. Why? Just to make your life a little bit easier. And from the beginning we have dx dt, which was also defined everywhere continuous, plus df dy at the same point times dy dt. Notice what happens here with these guys looking diagonally, staring at each other. Keep in mind the plus sign. And of course some of you told me, well, is that okay? You know my favorite, right? F sub x at x of t, y of t. That's fine. I saw that in engineering you use, and physics majors also, use a lot of this notation, sub f sub x, f sub t. All right, we've seen that. We've seen that. It comes as no surprise to us, but we would like to see if there are any other cases we should worry about. Now, I don't want to jump to the next example until I give you something that you know very well from Calculus 1. An example that you saw before, there was a melting ice sphere. It appears a lot in problems like final exam problems and stuff. What is the material of this ball? It's melting ice. And if you remember, it says at the moment t0, assume the radius was 5 inches. We also know that the rate of change of the radius in time, the rate of change will be -5. What? Let's suppose that we say that inches per minute. It's really hot in the room, not this room, but the room, the hypothetical room where the ball is melting, the sphere ball, the ice ball is melting. So imagine in 1 minute the radius will go down by 5 inches. Yeah, it must be really hot. I want to know the derivative dv dt at the time 0. So you go, oh my God, I don't remember doing this. Actually, this is a Calc 1 type of problem. I'm not, why am I even discussing it again? Because I want to fool you a little bit into remembering the elementary formulas for the volume of a sphere, volume of a cone, volume of a cylinder. That was a long time ago. When you asked your teachers in K-12 if you should memorize them, they said, by all means, memorize them. That was elementary geometry. But some of you know them by heart, some of you don't. Do you remember the volume formula for a ball of radius R?
1/3 pi r cubed.
Huh?
Pi r cubed. 4/3.
Good. I'm proud of you guys. I've discovered lots of people who are engineering majors and they don't know this formula. So how are we going to think of this problem? We have to think chain rule. And chain rule means that you view this radius as a shrinking thing because that's why you have the rate of change negative. The radius is shrinking, it's decreasing, so you view this r as a function of t, and of course you made me cube it, I had to cube it. And then v will be a function of t ultimately, but you see guys, t goes to r of t goes to v of t. What's the formula for this function? V equals 4 pi r cubed over 3. So this is how the diagram goes. You look at that composition and you have dv/dt. And I remember teaching as a graduate student, that was a long time ago, 97 or something, 96, 97, with this kind of diagrams with compositions of functions. And my students had told me, nobody showed us this kind of diagram before. Well, I do. I think they are very useful for understanding how a composition will go. Now, I will just go ahead and say v prime because I'm lazy and I go v prime of t is 0, meaning that this is dv dt at t0. And somebody has to help me remember how we did the chain rule in Calc 1. Was ages ago, 4 pi over 3 constant times. Who jumps down? The 3 jumps down, and he's very happy to do that. 3 r squared, but r squared is not an independent variable. He depends, or he or she depends on t. So I'll be very happy to say 3 constant times, and that's the essential part. I'm not done. dr dt. So I have finally applied the chain rule, and how do I plug in the data in order to get this as the final answer? I just go 4 pi over 3 times what? 3 times r. Who is r at the time t0, where I want to view the whole situation? R squared at time t0 will be 25. Are you guys with me? dr dt at time t0 is -5. All right, I'm done. Well, okay, so you are going to ask me, if I'm taking the exam and I leave this in the exam like that, is it? Oh, it depends on the exam. If you have a multiple choice where this is simplified, obviously it's not the right thing to forget about it, but I will accept answers like that. I don't care about the numerical part very much. You can, if you want to do more, 4 times 25 is 100 times 5, so I have minus what? 500 pi. And okay, what would be the unit of that? I'm wondering. Cubic inches per minute. Very good. Cubic inches per minute. Why don't I write it down? because I couldn't care less. I'm a mathematician. If I were a physicist, I would definitely write it down. Okay? And he's right. Okay, now, you are gonna find this weird. Why is she doing this review of this kind of melting ice problem from Calc 1? Because today I'm being sneaky and mean, and I want to give you a little challenge for 1 point extra credit. You will have to compose your own problem in Calculus 3 that is like that. So you have to compose a problem about a cylinder, full cylinder, how do I say that? Solid cylinder made of ice. Say what, Magdalena? Okay, so I'll write it down. Solid cylinder made of ice. That's melting in time. So compose your own problem. Well, do you have to solve your own problem? Yeah, I guess so. Once you compose your own problem, solve your own problem. For extra credit, 1 point. Compose, write, and solve. Write. You are a problem author. Write and solve your own problem. So that the story includes includes, instead of a nice ball, a solid cylinder, and necessarily, you cannot write just like a story. I once had a ice cylinder and it was melting, and I went to watch a movie, and by the time I came back it was all melted. That's not what I want. I want, and so that the problem is an example of using, applying the chain rule in Calc 3. And I won't say more. So maybe somebody can help with a hint. Maybe I shouldn't give too many hints. But let's talk as if we were chatting in a cafe without me writing too much down. Of course you can take notes of our discussion, but I don't want to have it documented. So we have a cylinder, right? That cylinder, there's the cylinder. Forget about this. So there's the cylinder. It's made of ice, and it's melting. And the volume should be a function of two variables, right? Because otherwise you don't have it in Calc 3. So function of two variables. What are the two variables that I'm talking about? The radius would be one of them. You don't have to say x and y. This is r and h. So h and r are in that formula. I'm not going to say which formula. You guys should know the formula of the volume of the cylinder. But both h and r, what do they have in common in the story? They are both functions of time. They are melting in time. Okay.
Quick question.
Yes, sir.
What did we solve for? What is the negative 500 pi?
This is the speed with which the volume is shrinking at time t0. Okay, so the rate of change of the volume at time t0. And this is something, by the way, that's what I would like you to, how I would like you to state it. Find the rate of change of the volume of the ice, what was that again, cylinder? At time t0, if you know that at time t0, something happens. Maybe r is given, h is given, the derivatives are given. You only had one derivative given here, which was r prime of t is minus 5. Now I leave it to you. I ask it to you and I leave it to you, and don't tell me. when we have a piece of ice, well, there was something in the news, but I'm not gonna say. Some nice ice sculpture in the news, yeah, okay. All right, so do the dimensions decrease at the same rate, do you think? I mean, I don't know, it's all up to you. Think of a case when the radius and the height would shrink at the same speed, and think of a case when the radius and the height of the cylinder made of ice would not change at the same rate for some reason. I don't know, but the simplest case would be to assume that all the dimensions shrink at the same speed, at the same rate of change. Okay? All right. So you write your own problem, you make up your own data. Now you will appreciate how much work people put into that web work. And if there is a bug, it's 1 in 1,000. But for a programmer to be able to write those problems, he has to know calculus, he has to know C++ or Java, he has to be good. That's not a problem, right? Then he or she has to know the how to write a problem so that you guys, no matter how you input your answer, as long as it is correct, you get the okay. Because you can put answers in many equivalent forms, and all of them have to be
Right answer.
yes, to get the right answer. So since I have new people who just came, and I understand you guys come from different buildings, and I'm not mad for people who come in late, because I know you come from other classes. I wanted to say we started from a melting ice sphere example in Calc 1 that was on many finals in here at Texas Tech. And I want you to compose your own problem based on that, this time involving a cylinder made of ice, whose dimensions are doing something special. Okay? That shouldn't be hard. I'm going to erase this part because it's not the relevant one. I'm going to keep this one a little bit more for people who want to take notes. And I'm going to move on. Another example we give you in the book is the one where x and y, the variables of the function f, are not just functions of time t, okay? They themselves are functions of other two variables. Is that a lot more different from what I gave you already? No. The idea is the same, and you are imaginative, you are able to come up with your own answers. I'm going to ask you to think what I'll have to write. This is finished. Okay. So assume that you have function z equals f of x, y. As we had it before, this is example, God knows, 2, where x is a function of u and v itself, and y is a function of u and v itself. And we assume that all the derivatives, all the partial derivatives are defined and continuous, and we make the problem really nice. And I will come up with some example that you know from before, where x equals x of uv equals uv, and y equals y of uv equals u plus v. So these functions are the sum and the product of other variables. can you tell me how I am going to compute, I'm going to compute the derivative of z or of f with respect to u at x of u v, y of u v? Is this hard? I don't know. You have to help me because why don't I put d here?
It's not funny.
Because you have two. So the composition in itself will be a function of two variables. So of course I have del. I'm going to go ahead and do it as you say. Without rushing, of course I know you are watching. What do we have?
2x into y.
No, in general. Oh, here I know you want to do it right away, but I would like you to give me a general formula mimicking the same thing you had before when you had one parameter t. Now you have u and v separately. You wanted to do it straight. So we have df dx at x of u v, y of u v. Shut up, Magdalena. Let people talk and help you because you're tired. It's a Thursday. df dx. dx, again del notation, partial with respect to u, plus df dy. So the second argument, so I prime with respect to the second argument, computing everything in the end, which means in terms of u and v, times again the dy with respect to u, you're saying that. Now, I'd like you to see the pattern. Of course, you see the pattern here, you're smart people, but I want to emphasize the cowboys. And green for the other cowboy, I'm trying to match the colors beautifully. And the independent variable, Mr. U, not you, but Mr. U, yes ma'am.
Is it the partial of dx du or is it dx du? Like you did the partial for the.
So,
and I thought in the
did
formula.
I do anything wrong? I don't think I did anything
So it is
wrong.
the partial for dx over du.
So I go df with respect to the first variable
Yes.
times that variable with respect to u.
But is it the partial? That's my question.
But it has to be a partial because x is a function of u and v.
Okay.
So I cannot put d,
Okay.
right? And then the same plus, the same idea as before, df with respect to the second argument times that second argument with respect to the u. You see, Mr. U is replacing Mr. T. He is independent. He's the guy who is moving. We don't care about anybody else, but he replaces the time in this kind of problem. All right? Okay. Now, the other one, I will let you speak. For df, dv, the same idea, but somebody else is going to talk.
It's going to be del f, del y.
Del f, del x. Well, I
yeah,
tried to
you know,
start in order. And I try to be organized and write neatly because I looked at, so these videos are in progress, and I'm trying to see what I did well or not, and I didn't, and at times I wrote neatly, at times I wrote not so neatly. I'm just learning about myself. It's one thing what you think about yourself from the inside, and to see yourself the way other people see you from the outside. It's not fun.
Say it again.
This is V. Okay. So I'll say it again. We all have a certain impression about ourselves, but when you see a movie of yourself, you see the way other people see you,
Oh,
and it's not fun.
so why do you, oh,
So So let's see the Cowboys. Ryan is looking at the map. He is all map. And Y is here, right? And who is the time variable kind of this time? This time is which one is the time? V and V is the only ultimate variable that we care about. So everything you did before in T with respect to T, you do before with respect to you do now with respect to you do now with respect to V. It shouldn't be hard to understand. I want to work the example, of course, with your help. I will work it. Now, remember how my students cheated on this one? So I told my colleague, he did not say by first writing the chain rule 5 years ago or 6 years ago, by first writing the chain rule for functions of two variables, express all the df, du, df, dv, but he said by any method. Of course, what they did, they were sneaky. They plugged in, they took something like x equals uv, they plugged it in here. They took the function in uv, they plugged it in here. They computed everything in terms of u and v and took the partials.
Why don't you do that way?
Well, it depends how the problem is formulated.
So make it the way, then just
Yeah.
plug it in.
So when they give you the precise functions, you're right. But if they don't give you those functions, if they keep them a secret, then you still have to write the general formula. If they don't give you the functions, all of them explicitly to you. Okay. So let's see what to do in this case. df du at x of u v y of u v will be what? Now, people help me please. So, I want to teach you how engineers and physicists very often express those at x and y. And many of you know because we talked about that in office hours. 2x, am I right? But evaluated at. And this is a very frequent notation in engineering world and physics majors world. So 2x evaluated at where? At the point where x is uv and y is u plus v. So I say I'll say x of uv, y of uv. And I'll replace later because I'm not in a hurry. dx du. Who is dx du? The derivative of x with respect to u. Are you guys awake?
Yes. So
Okay. V, very good, V. Plus, the next term, who's gonna tell me what we have?
2y evaluated.
2y evaluated at, and look how lazy I am, times the derivative with respect, the derivative of y with respect to u. So you were right, because it's 1. Attention, right? So it's dy du is 1. It's very easy to make a mistake. I've had students who make mistakes in the final from just miscopying, because when you are close to some formula, you don't see the whole picture. Just, what do? At the end of your exams, go back and, rather than quickly turning in a paper, never do that. Go back and check all your problems. It's a good habit. 2 times x, which is uv. I plug it as a function of u and v, right? Times of v plus, who is 2y? That's the last of the Mohicans. 1 is out. 2y. 2 times, replace y in terms of u and v, and you're done. So, do you like it? I don't. How would you write it? Not much better than that, but at least let's try 2uv squared plus 2u plus 2v. You can do a little bit more than that, but If you want to list it in order of degrees of the polynomials, that's okay. Now, next one, df dv, x of uv, y of uv. Such examples are in the book. Many things in the book and out of the book. I mean, in Webboard. Give you, I don't know why so many, give you combinations of this type, u plus v, u minus v. 2u plus 2v, 2u minus 2v. Well, I know why, because that's a rotation and rescaling. So there is a reason behind that, but I thought of doing something different for you. df dv. Now, what do I do? df dx. Again, the same thing, 2x evaluated at whoever times
U.
which, because you have dx with respect to v, so you have u, plus df dy, which is 2y, evaluated at the same kind of guy. So all you have to do is replace with respect to u and v. And finally multiplied by dy dv is 1 again. Just pay attention when you plug in, because you realize you can know this very well and understand it as a process. Make an algebra mistake, everything is out. And then you send me an email, say, I've tried this problem 15 times, and I don't even hold you responsible for that, because I can make algebra mistakes anytime. Okay, so 2uv times u plus 2 times u plus v. So what did I do here? I simply replaced the given functions in terms of u and v, and I'm done. Do I like it? No, but I'd like you to notice something as soon as I'm done. Tu squared v plus 2u plus 2v. Could I expect that? Could I have expected that? Look at the beauty of the functions. Z is a symmetric function. X and y have some sort of symmetry as well. If you swap u and v, and these are symmetric polynomials of order 1, of order 2 and 1 when product and stuff. Swap the variables, you still get the same thing. Swap the variables u and v, you get the same thing. So how could I have imagined that I'm going to get, without doing all this work, if I were smart, without doing all the work, I could figure out this by doing just what? By swapping the u and v, the roles of u and v. I would have said 2v u squared, 2v plus 2u, and it's the same thing I got here. But not always are you so lucky to be given nice data. Well, in real life, it's a mess. If you are, let's say, working with geophysics, real data, you have 2 parameters, and you have for those each parameter x and y, you have other 2 parameters. You will never have anything that nice. You may have nasty truncations of polynomials with many, many terms. That you work with approximating polynomials of the type Taylor or something like that. So don't expect these miracles to happen with real data, but the process is the same. And of course there are programs that incorporate all the Calculus 3 notions that we went over. There were people who already wrote lots of programs that enable you to compute derivatives of functions of several variables. Okay. Okay, all right. Now, any question? Okay, now let me take your temperature again. Is this hard? No. It's sort of logical. You just have to pay attention to what? Pay attention to not making too many algebra mistakes, right? That's kind of the idea. Okay. More things that I wanted to. There are many more things I wanted to share with you today, but I'm glad we reached some consensus in the sense that you feel there is logic and order in this type of problem. All right, now. I try to give you a little bit of introduction to why the gradient is so important last time. And I'm going to come back to that again. So I'm not going to leave you in the air. But before then, I would like to do the directional derivative, which is a very important section. So I'm going to start again. And I'll also do, at the same time, some review of 11.5. So I will combine them. And I want to introduce the notion of directional derivative because it's right there for us to grab it. And you say, well, that sounds familiar. It sounds like I dealt with direction before, but I didn't know what that was. That's exactly true. You dealt with it before, you just didn't know what it was. And I'll give you the general definition, but then I would like you to think about it. Have you ever seen that before? Okay, so let's say I'm going to say I have the derivative of a function f in the direction u, and I'm gonna put u bar as if you were free, not a married man, but u as a direction is always a unit vector. I told you last time, just to prepare you, direction u is always, but always a unit vector. Always. Compute it at x0, y0. x0, y0 is a given point, p point. And I'm going to say what that's going to be. I have limit, I'm going to use the h. And you say, why in the world is she using h? You will see in a second h goes to 0 because we haven't used h in a while. H is like a small displacement that shrinks to 0. And I put here f of x0 plus h u1, comma, y0 plus h u2, close, minus f of x0, y0. So you say, wait a minute, Magdalena, oh my God, I get a headache. I'm not here. Z0 is easy to understand for everybody, right? That's going to be the altitude at the point x0, y0. It shouldn't be hard. On the other hand, what am I doing? I have to look at a real graph in the real world, and that's going to be a patch of a surface, patch of a smooth surface. And I say, okay, this is my favorite point. I have x0, y0 on the ground, and the point, corresponding point P in 3 dimensions will be x0, y0, and z0, which is the f of x0, y0. And you say, wait a minute, what do you mean like I'm moving in a direction? Is it like when we drove, when we didn't drive, when we sled with, we took a sleigh and we went to have fun on the hill? Yeah, but I said that would be the last time we talked about the hilly area with snow on it. It was a good preparation for today in the sense that, remember, we went somewhere, an arbitrary direction, northeast, I plus j, and in the direction I plus j, which is not quite the direction, and I'll ask you why in a second, I was going down along a meridian, remember last time, and then that was my steepest direction of descent, the direction of the steepest descent. I was sliding down. If I wanted the direction of the steepest ascent, that would have been minus I minus j. So I had plus I plus j, minus I minus j. And I told you last time, why are those not quite directions? They are not unitary. So to make them like this u, I should have said, in the direction I plus j, that was 1 minus x squared minus y squared, the paraboloid, that was the hill full of snow. So in the direction I plus j, I go down the steepest possible, the fastest possible way. In the direction I plus j over square root of 2, I would be fine with the unit vector. In the opposite direction, I go up the fastest way possible, but I didn't want to because it's, I mean, imagine hiking the steepest possible direction, the steepest way. All right. Now, with my direction? My direction in plane should be a vector. And that magic vector should have length 1 from here to here. When you measure this guy, he has to have length 1. And if you decompose, you have to decompose him, right? Along the what is this? The x direction and the y direction, right? How do you split a vector in such a decomposition? Well, Mr. U will be U1i plus 1i, sounds funny, plus U2j. So you have U1 from here to here. I don't know how well can you draw. Can you? I think some of you can draw really well, especially better than me because you took technical drawing, right? And how many of you took technical drawing in this class?
Not this class?
In anything, high school or college?
Towards the middle school. So it gives it two-dimensional, you have to draw this schematic. So
It's really helping you with a perspective view, 3D view from an angle, right? So now you're looking at this u direction as being u1i plus u2j. And you say, okay, I think I know what's going on. You have a displacement in the x-coordinate in the direction of u, in the direction of the x-coordinate by 1 times h, so a small displacement you are talking about. And, yes?
Why 1 times h? Where does 1 come from? Like you just
One,
said
which
time.
one?
You said like 1 times h.
u1,
Okay.
u1,
Okay.
u1. You will see in a second. That's the way you define it. This is just a definition. I would like you to tell me what the whole animal is if I want to represent it later, and if you can give me some examples. And if I go in the y direction with a small displacement, I have from y0, I have to leave and go, so I am here at x0, y0, right? And this is the x direction and this is the y direction. And when I displace a little bit, I displace with the green. I displace in this direction, I will have to displace and see what happens here, right? And then in this direction, I'm not going to write it yet. So I'm displacing in this direction and in that direction. Why am I keeping it h? Well, because I have the point x0, y0 plus, how do you give me a collinear vector to u, but small one? You say, wait a minute, I know what you mean. I start from the point x0, this is p, plus a small multiple of the direction you give me. So here you had it before in Calc 2, you had t times, what was it, u1, u2, which is my vector u. So give me a small displacement vector, a very small displacement vector. in the direction u, which is u1, u2. u2 as a vector. You like angular brackets, I don't, but it doesn't matter.
So basically,
the c is x0 plus. You want t or h? T or h doesn't matter. H u1, ui0 plus h u2. Why not t and I take h? It is like time parameter that I'm doing with h, but h is a very small time parameter. It's an infinitesimally small time. It's just a fraction of a second after I start. That's why I use little h and not little t. It's a very tiny. H in general indicates a very small time displacement. Okay? So what I'm gonna have, I try to say, where am I here? I'm here just one step further with a small displacement, and that's gonna be p at this whole thing. This is, let's call it, okay, let's call this f of, this is, the blue one is f of x0, y0. And the green altitude, or the altitude of the green point, will be what? Well, this is something, something, and the altitude would be f of x0 plus hu1, y0 plus hu2. And I measure how far away the altitudes are. They are very close. The blue altitude and the green altitude, there is a displacement. How can I draw that? Here. You see this one? This is the delta z. So this thing is like a delta z kind of guy. Any questions? It's a little bit hard. You'll see it in a second. Yes, sir.
it's like the smaller displacement, it has to be perpendicular to the line of action, which is u.
No,
It's a resultant of u.
it is in the direction. So,
In the direction.
so let's model it better. I don't have a three-dimensional. They sent me an email this morning from the library saying, do you want a three-dimensional print? Do you want to support the idea of Texas Tech having a three-dimensional printer available for educational purposes?
You say, of course you
Well,
do.
of course I want. But I don't have a three-dimensional printer, but you have imagination, and imagine we have a surface that again looks like a hill. Oh, that's my hand. And this engagement ring that I have is actually P0, which is x0, y0, z0. And I am going, well, I'm going in a direction of somebody. It doesn't have to be you, not nothing personal. So I'm going in the direction of u1, u2 is that horizontal thing. I'm going in that direction. So this is the direction I'm going in. And I say, okay, where do I go? Where do a small displacement? Infinitesimally small displacement in that direction, here I am. So the 2 points are related to one another, and you say, but there's such a small difference in altitudes because you have an infinitesimally small displacement in that direction. Yes, I know, but when you make the ratio between that small delta z and the small h, the ratio could be 65, 120, minus 32. You don't know what you get. So you, just like in general difference of limit of the difference quotient being the derivative, you get the ratio between some things that are very small. But in the end, you can get something unexpected, finite or infinite. Now, what do you think this guy will be? According to your previous chain rule preparation, I taught you about chain rule. How do we, what will this be if we compute the, there is a proof for this. It would be like a page or a 2-page proof for what I'm claiming to have. Or what, how do you think I'm going to get to this without doing the limit of the difference quotient? Because If I give you functions and you do the limit of the difference quotient for some nasty functions, you'll never finish. So what do you think we ought to do? This is going to be some sort of derivative, right? And it's going to be a derivative of what? Yes, sir.
Well, it's going to be a partial, it's going to be like a partial derivative, except the plane you're using to cut the surface is not going to be in the x direction or the y direction. It's going to be along u.
Right. So that is a very good observation. It would be like I would do the partial in, not in this direction, not in that direction, but in this direction. Okay. Let me tell you what this is. So according to a theorem, this would be df dx, exactly like the chain rule, at my favorite point here, x0, y0, that was p, times. Now you say, oh, Magdalena, I understand. You're doing some sort of derivation. The derivative of that with respect to h would be u1. Yes, it's a chain rule. So then I go times u1 plus df dy at the point times u2. And you say, okay, but that's, can I prove that? Yes, you could. But to prove that, you would need to play a game. The proof will involve that you multiply up and down by an additional expression, and then you take limit of a product, and you take the product of the limits, and you study them separately until you get to this. So this is an application of the chain rule. But I want to come back to what Alexander just noticed. I can explain this much better if we only think of derivative in the direction of I and derivative in the direction of j. What the heck are those? What are they gonna be? The directional derivative if I had I instead of u. And that will make you understand the whole notion much better. So what would be the directional derivative of f in the direction of I only? Well, I for an I goes this way. This is a hard lesson. And it's advanced calculus rather than calculus 3, but you're going to get it. So if I go in the direction of I should have the df dx, right? That should be it. Do I?
Yes,
I mean, was I able,
exactly.
was I able to invent something so when I come back to what I already know, I recreate the f dx and nothing else? Precisely, because what will be for I as being u? What will be u1 and u2? u1 is 1, u2 is 0, right? Because when we write I as a function of I and j, that's 1 times I plus 0 times j. So u1 is 1, u2 is 0. Thank God. According to anything, this difference quotient or the simpler way to define it from the theorem would be simply the second guy goes away, it vanishes. u1 will be 1, and what I'm left with is df dx. And that's exactly what Alex noticed. So the directional derivative in is defined such as a combination of vectors, such that you recreate the directional derivative in the direction of I being the partial df dx, exactly like you learned before in 11.3. And what do I have if I try to recreate the directional derivative in the direction of j? 0i0. We don't explain this much in the book. I think I think at this one I'm doing a better job than the book. So what is df in the direction of j? J is this one. Well, if j is that 1j, let me write it down, is 0i plus 1j. 0 is u1, 1 is u2. So by this formula, I have simply that I should get directional derivative in the direction of, with respect to, directional derivative is the partial derivative with respect to y at my point times a 1 that I'm not going to write. So it's a concoction. It's a concoction so that in the directions of I and j, you actually get the partial derivatives. And everything else is linear algebra. So if you have a problem understanding the composition of vectors, the sum of vectors, this is because U1 and U2 are scalars, I'm sorry. This is because you haven't taken the linear algebra yet, which teaches you a lot about how a vector decomposes in two different directions or along two bases, the standard canonical basis. Okay, let's see some problems of the type that I've always put in the midterm and the same kind of problems like we have seen in the final. Example 3, is it guys? I don't know, example 3, 4, something like that. Given z equals f of x, y, what do you like best, the valley or the hill? This appeared in most of my exams. X squared plus y squared, circular paraboloid was one of my favorite examples. 1 minus x squared minus y squared was the hill, the circular paraboloid upside down. Do you prefer, which one do you prefer? I don't care. Which one? The hill, the first one? It's easier? Okay. Okay. And typical problem. Compute the directional derivative of z equals f of x and y at the point P of coordinates 1, 1, 2 in the directions, in the following directions. A, I, B, J, C, I plus J, D, I plus J over square root 2, sorry, D, the opposite, minus I minus J over square root of 2, and E, I'm
That's
gonna,
square root of 3.
what?
You wrote a square root of 3.
I wrote square root of 3. Thank you guys, thanks for being vigilant. So, always keep an eye on me, because I'm full of surprises, good and bad, no, I'll just kidding. Okay, so let's see, what do I want to put here, something, how about this? Over root 5 I plus 4 over root 5j. Is this a unit vector or not?
Yeah, it is a unit vector.
Why is that a unit vector?
It's missing, no, it's not. It's
And how do I make it a unit vector?
I have to
Move
take,
the
Yeah, multiply that square root of 5.
I have to take the 3, it has to be 1.
3.5.
And the second one has to be 1 on the top to make it a unit vector.
You can do 3 over 5 before.
Give me a unit vector. Another one, then they stay these easy ones.
3 over 5 and 4 over 5.
Huh?
3 over 5i and 4 over 5j.
3 over, I cannot hear. 3 over 5
And 4 over 5.
And 4 over 5j.
and 4 over
That's right.
5. And why is that a unit vector?
Because 3 squared plus 4 squared.
And what do we call these numbers? You say, what is that, an interview? Yes, it is an interview. Pythagorean numbers. 3, 4, and 5 are Pythagorean numbers. Okay. Alrighty, so let me think a little bit where I should write. Is this seen by the, yes, it's seen by the, I'll just leave what's important for me to solve this problem. Hey, So what do we do? The same thing. I is 1 point I plus 0, or 1 times I plus 0 times j. So simply, you can write the formula, or you can say, the heck with the formula, I know df is df dx. The derivative of this at the point P. So what you want to do is say 2x. Are you guys with me? At the value 112, which is 2. And at the end of this exercise, I'm going to ask you if there is any connection between, or maybe I will ask you next time. Oh, we have that. What is d in the direction of j? The partial derivative with respect to y. Nothing else but our old friend. And our old friend says I have 2y computed for the point P 1, 1, 2. What does it mean? Y is 2, y is 1. So just plug this 1 into the thingy. It's 2. Now, do I see something? I'm a scientist. I have to find interpretations when I get results that coincide. It's a pattern. Why do I get the same answer?
Because your function is symmetric.
Right, and more than that, because the function is symmetric. It's a quadric that I love. It's just a circular parabola. Its rotation is symmetric. So I just take one parabola, one branch of a parabola, and I rotate it by 360 degrees. So the slope will be the same in both directions, I and j, at the point that I have. If the, well, okay, it depends on the point. If the point is itself symmetric, like that, x and y are the same, 1 and 1, I did it on purpose. Okay, if you didn't have 1 and 1, you had an x variable and a y variable to plug in. But your magic point is where? Oh my God, I don't know how to explain with my hands. Here I am, the frame. I'm the frame. X, Y, and Z. 1, 1. Go up. Where do you meet the vase? At Z equals 2. So it's a really symmetric, really beautiful picture. Now, next, I say, oh, in the direction I plus j, which is exactly the direction of this meridian that I was talking about. I plus j over square root 2. Now, I've had students, and that's where I was broken-hearted. Really, I didn't know what to do, how much partial credit to give. The definition of directional derivative is very strict. It says you cannot take whatever you want and you want. You cannot multiply them by proportionality. You have to have u to be a unit vector, okay? And then the directional derivative will be unique. If I take 1 and 1 for u1 and u2, then I can take 2 and 2 and 7 and 7 and 9 and 9, and that's going to be a mess because the directional derivative wouldn't be unique anymore. And that's why whoever gave this definition, I think Euler, I tried to see in the history who was the first mathematician who gave the definition of the directional derivative. And some people said it was Gateau because that's a French mathematician who first talked about the Gateau derivative, which is like the directional derivative. But other people said, no, look at Euler's work. He was a genius. He's the guy who invented the number E, right? Who discovered the transcendental number E, and many other things. And the exponential, e to the x, is also from Euler and everything. He was one of the fathers of calculus. Apparently, he knew the first 32 decimals of the number E. And how he got to them is by hand. Do you guys know any of them? 2.71828, and that's all I know. first five decimals. Well, he knew 32 of them. And he got to them by hand. And they are non-repeating infinitely many decimals. It's a transcendental number.
And his 32 were correct? His 32 were correct?
His first 32 decimals were correct. I don't know what, I mean, the guy was something like he was working at night, okay? And he would fill out in one night hundreds of pages, computations, both by hand formulas and numerical. So imagine, of course, he would never make a web war mistake. I mean, if he were to come, we build the time machine and we bring Euler back in here, Texas Tech, and we make him solve our web war problems, I think he would take 1,000 problems, solve them in one night. He needs to know how to type. So we have to teach him how to type. But he would be able to compute what you guys have, all those numerical answers, in his head. He was a scary fellow. So U has to be unicized in some way, made unique, right? U1 and U2. I had students, that's where the story started, who were very good, very smart, both honors and non-honors, who took U1 to be 1, U2 to be 2, because they thought direction 1, 1, which is not made unique as a direction, unity, right? And they plugged in here 1, they plugged in here 1, they got this correctly. What was I supposed to give them as a grade? Huh? I gave them how much do you think? Nitish, you know me a little.
I don't know.
Full.
60%. No, I think some people don't give any credit. So pay attention to this. In this case, this has to be 1 over square root of 2 times the derivative of f at x, which is computed before at the point, plus 1 over square root of 2 times the derivative of the function, again computed the same place, which is, oh my God, square root of 2 plus square root of 2, which is 2 square root of 2. All right. And finally, the derivative of f at the same point, I should have put at the point, like a physicist would say, at p, to make you familiar with this notation. And then measured at what? The opposite direction, minus I minus j. And now I'm getting lazy, and I'm going to ask you what the answer will be.
U minus 2.
So you see, there is a pattern, another pattern. In the opposite direction, the directional derivative in this case would just be the negative one. What if we took this directional derivative in absolute value? Because you see, in this direction is a positive directional derivative. In the other direction, well, it's because, I know why. I'm a vase, right? So in the direction I plus j over square root of 2, the directional derivative will be positive. It goes up. But in the direction minus I minus j, which is the opposite over square root of 2, it goes down. So the slope is negative. So that's why we have negative. Everything you get in life or in math, you have to find an interpretation. Okay? Sometimes, like in mathematics, things are subtle. People say one thing and they mean another thing. You have to try to see beyond their words. That's sad. And in mathematics, you have to try to see beyond the numbers. You see a pattern. So in opposite directions, I got opposite signs of the directional derivative because I have opposite slopes. All right, good. What else do I want to learn in this example? One last thing. I have
E.
E. I still have that. So I have the same thing. It's going to be, so it's not going to matter. The direction is the only thing that changes. These guys are the same. The partials are the same at the same point. I'm not going to worry about them. So I get 2 for both. What changes is the blue guys. It's going to be 3 over 5. and 4 over 5. And what do I get? I get, oh, right? Okay, now, I want to tell you something. I already anticipated something last time. And let me tell you what I said last time. Maybe I should not erase, but I have to erase this whether I like it or not. And I'll review what this was. What is this? Z equals x squared plus y squared, yes or no?
Yes.
Okay. So, what did I say last time? We have the result. We noticed it last time. We did not prove it. We did not prove it. Only found it experimentally. Using our physical common sense. When you have a function z equals f of x, y, we studied the maximum rate of change. Rate of change at the point x0, y0 in the domain. Assuming this is a C1 function item, maximum rate of change was a magic thing. And you probably thought, what in the world is that? And we also said this maximum for the rate of change is always attained Magdalena, can you say attained? Attained. Oh. Is this correct? Okay. In the direction of the gradient. So you realize that it's the steepest ascent, the way it's called in many other fields but mathematics, all the STEM fields, or the steepest descent. Now, if it's an ascent, then it's in the direction gradient of f. But if it's a descent, it's going to be in the opposite direction, minus gradient of f. But then I say, first of all, it's not the same direction if you have opposites. Well, direction is sort of given by one line. Whether you take this or the opposite is the same thing. What worries me is that we say direction and we didn't unitarize it. So we could say or gradient of f over length of gradient of f, or minus gradient of f over length of gradient of f. Can this theorem be proved? Yes, it can be proved. We are going to discuss a little bit more next time about it, but I want to tell you a big disclosure today. This maximum rate of change is the directional derivative. This maximum rate of change is exactly the directional derivative in the direction of the gradient. Which is also the magnitude of the gradient. And you say, wait a minute, what? What did you say? Let's first verify my claim. I'm not even sure my claim is true. We will see it next time. Can I verify my claim on one example? Well, okay, maximum rate of change would be exactly as the directional derivative in the direction of the gradient. I don't know about that, that sounds crazy. So what do I have to compute? I have to compute the directional derivative of, let's say, my function f in the direction of the gradient. What is the gradient? We have to figure it out. We done it last time, but you forgot. So for this guy, nabla f, what will be the gradient? Now, where is my function? Nabla f will be 2x to y, right? Which means 2xi plus 2yj, right? But if I'm at the point P, what does it mean? At the point P, it means that I have 2 times I plus 2 times j, right? And what is the magnitude of the gradient? Yes, the magnitude of the gradient is somebody I know, which is what? Which is square root of 2 squared plus 2 squared. I cannot do math now. Square root of 8. What's square root of 8? 2 root 2. This is a pattern. 2 root 2. I've seen this 2 root 2 again somewhere. Where the heck have I seen it?
That was the directional derivative.
The directional derivative. So the claim may be right. It says it is the directional derivative in the direction of the gradient. But is this really the direction of the gradient? Yes. Because when you compute the direction for the gradient 2i plus 2j, you don't mean 2i plus 2j as a twice I plus j. You mean the unit vector corresponding to that. So what is the direction corresponding to the gradient 2i plus 2j? Is this exactly u equals I plus j divided by square root 2. So this is the directional derivative in the direction of the gradient at the point P, which is 2 root 2, and it's exactly the same thing as the, for some reason, that's mysterious, and we will see next time. For some mysterious reason, you get exactly the same as the length of the gradient vector. Okay? We will see about this mystery next time. I gave you enough to torment you until Tuesday. What have you promised me besides doing the homework? To read the book. You're very smart. Please read the book. All the examples in the book that I showed. Okay, thank you so much. Have a wonderful weekend. And I'll talk to you on Tuesday about anything you have trouble with. When is the homework due? On Saturday. I was mean. I should have given you until Sunday night, but I think you want me to make it until Sunday night at midnight? Okay, I'll do that. I'll exchange. I will extend it a little bit.
She asked, I said yes.
Why'd you do that, dude? Come on, my life is ruined now. Because I have more time to work on my homework.
And that will ruin your Sunday.
Yeah, no.
No. Actually, I know why I did that. I thought 28th of February is the last day of the month. But it's a short month, so he's right. We have to extend the months a little bit by pulling it by one more day.
We did?
It's 1st of March is Sunday, right?
Yeah.
That's awesome.
Sure. Yeah. What are you going to do?
This is speech.
You're in English?
Uh-huh.
You don't know English? Why are you taking English? That's what my father used to say. You don't know your own tongue?